Now that we've set ourselves up with our Schrödinger equation, some basic mathematics of eigenfunctions, orthogonality, and completeness, and we've solved a fairly easy but important problem of the infinitely deep well, or the particle in a box, we can tackle some slightly more realistic problems, and we're going to look at two important ones here. First, we will look at a particle in a rectangular well of finite depth. This is quite a realistic model for some quite practical situations. In fact, we come across this problem all the time when designing various modern optoelectronic devices, like semiconductor lasers and optical modulators that are based on so-called quantum well layered semiconductor structures. After looking at that problem, we will have a first look at the harmonic oscillator problem. That is actually the problem of a particle in a parabolic-shaped potential well. This problem is of very great use in quantum mechanics, as it occurs for all sorts of oscillating systems. For the moment here, as a start, we'll just be considering the non-oscillating aspects of this system. We can handle both of these problems mathematically, though compared to the simple particle in the box, they take a bit more algebra than that problem does. There are a few more problems that can be handled analytically, but for most more complicated problems we would just likely move over to solving them numerically, and we will get to that later. These two specific problems, though, of the finite potential well and the harmonic oscillator, are both worth solving analytically, though because these analytic solutions can give us significant insight, we're going to take some time to do them. The algebra is a bit more complicated, and we will be able to use that insight in quantum mechanical systems in general, as well as these particular problems being practically useful in their own right.